Welcome you all to this course on electron diffraction and imaging. Okay. In the last class, we gave some brief idea about how to construct different types of polar nets, okay, and how to use it to get some information. Okay. Let us just have a recap of what we have done so far. The first thing which we covered was what is the definition of a stereographic projection. Then the next aspect which we covered was what are the properties of the stereographic projection. The third is construction of polar and Wolf nets, which can be used to measure angular relationship between planes. Okay. The third is how to use this nets. That is what it is. There what all things which we covered. One, measurement of angle between poles, okay. Then rotation of poles around latitudes, okay. How to measure the angle, okay. Then the next is rotation of poles around the central pole, okay, how to do that, and the rotation of a pole around another pole which is not lying on the center of the stereogram, then how to go about and do this rotation. Okay. Then measurement of angle between poles lying on either latitudes or longitudes. Okay. Measurement of angle between poles not lying on either one is measurement of angle between poles which are lying on either latitude or longitude. Another is measurement of angle between poles which are lying not lying on either latitudes or longitudes. Okay. Then how to construct a great circle for a pole. Given a pole, how to construct a great circle for it. Okay. Then suppose two poles are there, how to draw a great circle which is passing through these poles. Okay. Then suppose the pole is given, how the opposite of the pole can be created on a stereogram. Okay. Another is marking of rotation points on the stereogram when the poles move from one hemisphere to another hemisphere. That is, suppose pole is being rotated in a stereogram, okay, it is moving beyond the projection hemisphere into that other hemisphere. In such cases, how to represent the position of the pole. These are all essentially the basic operations which are necessary to use the stereogram effectively. That is all which we have studied. This one has to do a lot of exercise, okay, practice it, okay, and that is the only way you can learn how to use that stereogram. Okay. Though I am just telling it how it is to be done, okay, unless and until you work out on some problems, okay, it is difficult, because this is stereogram is essentially supposed to be used get orientation relationship between planes and all these things. This is essentially something which has to be worked out, for which unless you do a lot of problem involving the various aspects of how to use the stereogram, one will not be able to understand it thoroughly. That is what I can give you some assignments later, and as you take this course you can go through do that assignment. That way you will be able to gain better understanding of how to use the stereogram. Okay. What is the basic definition of a stereogram? Okay. I mentioned first in the beginning that stereogram is nothing but a perspective projection, but it is a conditional one. The stereographic projection is nothing but projection of various points on poles on the surface of the sphere, okay, into a projection plane, and the projection plane is lying on a great circle, and using perspective projection, but the viewing point also on the surface of the sphere, but perpendicular to the projection plane. That is what essentially this is nothing but if this is a sphere, okay, if this is one of the projection plane, okay, then if we are viewing from this direction, all the points on this hemisphere, okay, their projection, okay, they cut this equatorial plane. These points are the ones, okay, which show the angular relationship in 3 dimensions, which is, okay, it's nothing but the angular relation in 3 dimensions which is projected onto a 2 dimension. So this projection is called as the stereographic projection. Instead of taking this plane, okay, we can take a plane which is just we can keep a sheet of paper here which is tangent to this axis of the north-south axis through which we are, or any axis for that matter. Suppose we are viewing it in this direction, then this will be kept here, and then this plane perpendicular to it, this is going to be the equatorial plane. So either this plane or this plane, or it is can be this plane or the plane which comes here, okay, whichever way, but this projection is called as that. So what is it being projected? All the points which are there only on the surface of the sphere which is getting projected. That one should understand. Okay, this is a subtle difference between the conventional perspective projection, where it is very difficult to get angular information, whereas in this particular projection the angular details are transferred onto the projection plane. Having learned so far, okay, how to measure angles under different circumstances, okay, let us look at how a stereogram can be constructed for a crystal. Here, if you see, this is a sphere in which a cube of a crystal is kept. Okay, we can assume this cube to be maybe a simple cubic structure. Okay, and with that center at the center. Okay, all the plane normals are drawn. Okay, from the various cube surfaces. They meet this. They cut the sphere on the some particular points. Okay, these are all, we call it as the poles corresponding to those planes. Okay, and these points are nothing but essentially the plane normals which are cutting the surface on a particular point. This point is called as the pole corresponding to that plane. Okay, and the plane which is passing through the center, okay, which is normal to this pole, if we extend this plane is going to cut the surface of the sphere. Okay, the one on which it cuts, always it will turn out to be a longitude or latitude, and this is what, as we discussed in the last class, this we call it as the great circle. Okay, so the great circle is nothing but the showing cut section of the plane, that is on the sphere, and this is essentially what is being shown here. This is a small plane, okay, that section which is cutting and creating the longitude, the great circle, and the normal to it, this is what the pole is. Suppose we wanted to measure an angle between two planes in this particular case. Okay, this is what the angle between these two planes, that same is equivalent to angle between the plane normals also. So by measuring the angle between the plane normals, essentially what we get is that angle between the planes. Okay, let us see how to construct a stereogram. In this particular case, okay, what has been done is that there we showed a one small cube. Okay, here we are drawing plane normals corresponding to a cube which has been kept at the center. Okay, the plane normals are cutting the surface of the sphere at different points and generate various poles. Okay, what is essentially important is that for example, suppose we see that for in this direction, for this pole 0 0 1 bar, okay, the great circle corresponding to it is this particular one. Okay, all the poles which are perpendicular to this pole, all will be lying on these great circles. So you can say that all the poles which are perpendicular to a specific pole lie on a great circle corresponding to that. So the great circle corresponding to various poles are also being shown in this diagram. They are all marked here. Okay, now what we can do it is that suppose we use this as the viewing direction. Okay, from this direction we are trying to view it. Okay, and look at all the poles which are lying on the northern hemisphere, and what is the point at which they are making intersections on this equatorial plane. Okay. That is what is being shown in this stereogram, in this view graph. Here you can see that these are all the various poles, and all these poles also, okay, should as we have discussed in the last class, the angular relationship between the various poles which are lying on the surface of the sphere, that is being maintained here. Okay. And if we see this projection plane, okay, that is what is the stereographic projection. That is the projection plane which is shown here. Okay. Now, if you look at this projection, okay, 0 0 1 is at the center, okay, that shows the center of that, because that is the point through which the axis passes through, north south axis, okay, and the 1 0 0 and 0 1 0, okay, are 90 degree away from it, because they are all going to lie on the primitive. As we can see here, this is lying on the primitive of this circle, okay. That is what essentially is being shown here, okay. But we know also that all the poles which are 90 degree away from it, okay, they should lie on this great circle, which is the primitive circle, okay. Then how to choose this specific direction, okay, that the convention which we follow for in crystallography, that is being used, that is from top to bottom it is the x, and from left to right it is the y direction, z direction is in this perpendicular to the screen. Okay. Then if we choose, if that is as per that stereogram which we have the previous slide, okay, the equatorial plane projection, this is one, this will be making an angle 90 degree with respect to it, and 110 plane comes like this. This is how the various planes will be coming, okay. And the great circles corresponding to other planes also, okay, their trace also could be seen in this stereogram. So, this stereogram generally is referred to as 001 stereogram, and here in addition to it, that symbol which is being shown here, this symbol corresponds to, it is a fourfold rotation which is associated with it. In this particular one, if we look at it, it has got a threefold rotation which is associated with it. This is along 111 direction, along 110 direction twofold rotation is there. So, all the symmetry elements also can be represented, each of the point what sort of symmetry element is around those directions, that also can be indicated on this stereogram. Okay. So, we assume that you assume that it is essentially nothing but a cube which has been kept, okay, and the various poles which it is making, it is cutting on the surface of that sphere, okay, and on the equatorial plane they make some poles corresponding to them. Okay. This is just a view graph of that which we are seeing it. Suppose now we wanted to find out what is the angle between these. We know that from the center to this one, this is 90 degree, from here to here, that is on the circle all the points are 90 degree away from that, that is all the information which we know. Okay. And now we wanted to measure the angle between these various planes. What we should do is, we should keep it in we should keep it on top of a wolf net. Okay. That is what essentially which has been done, on the wolf net which has been done. Now, okay, like we have to use what we have learned in the last class. Okay. That is, if you wanted to measure an angle between two poles, okay, that pole should be either lying on a latitude or on a longitude. Here these are lying on a latitude. So, we can directly measure the angle which is 45 degree from 001 to 011, okay, 011. Similarly, from here to 101, this is 45 degree. Okay. Then from here to here, we know that we can directly measure this along the circumference. This is another 45 degree, and from 010 to 110, this is 45 degree. Suppose we wanted to measure with respect to this particular point, then what we have to do it is, we rotate this the tracing sheet and bring this point to the, then we can measure, that will turn out to be 54 degrees, because this is all, this stereogram 001 standard stereogram is for a cubic crystal. Okay. This is the way we can use the stereogram and the wolf net to measure and find out angle between the planes. Okay. That is what we did as some exercise in the last class. Okay. But when we wanted to construct a stereogram, this is not the method we can go about and construct stereograms, okay, because this is a very nice thought experiment where we have kept a crystal at the middle of a cube and done this, because if we have to generate stereogram of like this, we have to take some photograph and go about and do it, which is not a practical way in which it can be done. Okay. There is another way in which we can compute the angles between the various planes in cubic system and generate a stereogram. That is what we will discuss now. You know that the angle between various planes, okay, can be determined using this formula between two planes, okay, which are related by vectors g1 and g2. The angle between them equals g1 dot g2, because g1 and g2 are in reciprocal space, g1 modulus of g1 into modulus of g2. Okay. G1 and G2 are essentially in the same direction as the plane normals. So, the angle between them gives the angle between the planes. This formula could be used. What will happen in the case of a simple cubic system? This one becomes H1 H2 plus K1 K2 plus L1 L2 divided by root of H1 squared plus K1 squared plus L1 squared into H2 squared plus K2 squared plus L2 squared. So, okay. Using this formula, angle between the various planes could be calculated. Same way, angle between, because we know that this is true only for the case of cubic system, because the lattice parameters does not figure in this case, okay. And also that plane normals, okay, and the directions have the same indices for cubic system, whereas for all other crystal structures, Bravais lattices, the plane normals and the directions, the crystals, they do not have the same indices, and because of that, okay, if we have to find out the angle between the planes, we have to use this formula cos theta equals, okay, that is for a simple orthorhombic case. If we consider, it will be H1 H2 by A squared plus K1 K2 by B squared plus L1 L2 by C squared, okay, divided by root of H1 by A the whole squared plus K1 by B the whole square plus L1 by C the whole square into H2 by A the whole square plus K2 by B the whole square plus L2 by C the whole square. This is how it will turn out to be. Okay. Okay. In this, the general formula is still valid, okay. But if you wanted to find out angle between the directions, then the cos theta will turn out to be R1 dot R2, where R1 and R2 direction vectors, the modulus of R1 dot modulus of R2. Okay. In the case of tetragonal lattice, okay, A will be equal to B, okay, then this formula will change accordingly. But what is essentially important is that in the case of all other lattices other than cubic lattice, okay, the angle between the planes depend upon the lattice parameter values. Okay. That one should keep it in mind. Okay. So, considering the case of a simple cubic system, okay, using this formula we can find out angle between the various planes, and these calculated values are given in this table. So, in this table if you look at it, this is here instead of H1 K1 L1, here it is used as HKL, that is capital and small letters are used to represent them. Okay. This is one plane 100, okay, and another plane Okay, if it is 1 0 0, angle between them becomes 0. For this we know all these results, so I will just write that between 1 0 0, okay, and 0 1 0, okay, or no, let us write between 0 0 1 and 0 1 0, or between 0 0 1 and 1 0 0, this angle is going to be 90 degree, okay. And similarly between 0 0 1 and 1 1 0, the angle is going to be 90 degree. Because this one can calculate and get it, I am just writing it down. Between 0 0 1 and 0 1 1, this angle is 45. Between 0 0 1 and 1 0 1, this angle is 45. Okay. If this turns out to be here 0 0 1 and 0 1 1 bar, then this angle will turn out to be 135 degree. Okay. These angles we can correctly measure and tabulate it. So, in fact, the information regarding these three, okay, with respect to 0 0 1 plane to other one 0 0 1 type of plane, 1 1 0 type of plane and 1 1 1 type of plane is sufficient. Because with respect to 1 1 1 plane, okay, that is 1 1 1 that all other that is 1 1 1 direction, if you take it, okay, this will be with respect to 0 0 1, okay, then 1 0 0 or 0 1 0, this makes an angle of 54 degree. Okay. Using this information, we can construct the stereogram for 0 0 1. That is what we will just study now. Okay. What has essentially been done is that since we are drawing a stereogram of 0 0 1, the 0 0 1 will come at the center of the stereographic projection. So, what we have done is taken the Wolf net, on top of it we have kept a stereogram, okay, drawn the primitive circle, okay, and then marked the these two axes x and y, okay, mark this point as 0 0 1. By convention, okay, 1 0 0 direction has to come here down, and 0 0 1 0 1 0 direction has to come in that y direction. Now, the angle between 0 0 1 and 1 0 0 is 90 degree. So, in this direction it should be 90 degree away. So, the pole will come here, okay. That is how we can mark this pole, and 0 1 0 pole will come here, and we can make out that from here to here along this circle, if you go, this is 90 degree it makes, okay. And then 1 1 0 plane, essentially if we look at it, that makes an angle 45 degrees with respect to 1 0 0 and also 45 degrees with respect to 1 1 0. Okay. That means that that has to come in between these two at an angle of 45 degree, and we know that from 0 0 1 1 1 0 is 90 degree. That means that 1 1 0 has to lie on this primitive circle. So, we can mark this point. Okay. So, now we have essentially got these points, okay, and we know that 0 1 1, okay, makes an angle of 45 degrees with respect to 0 0 1 as well as with 0 1 0. So, and that should lie on this equatorial line, okay, and that also we can make out that if 1 0 0 is a pole, okay, the great circle corresponding to it, which is 90 degree away from it, that is this line, and we know that 0 1 0 makes an angle of 90 degree with respect to 1 0 0. So, it should be lying on this line. So, since it is lying on a latitude, okay, on the equatorial plane, we can directly measure 45 degrees from here and mark it. Similarly, 0 1 bar 1 we can mark it. Okay. Then if we have marked 0 1 1, okay, we can draw a great circle corresponding to it, like the way we learned in that last class. Okay, we can draw a great circle corresponding to this particular one. We can draw another great circle. Similarly, 1001 will come in between this at 45. 1 bar 01 will come between 001 and 1 bar 00. Okay, at an angle of 45. So we can draw a great circle corresponding to it, and we know from the angular relationship that corresponding to 011, okay, all the poles which make an angle of 90 degree will be lying on these longitudes. Okay. Then if we know the angle between these planes, okay, since they are lying on the longitude, we can mark those points. This way we can mark all the points corresponding to it. Okay. And another like it that for example 1 bar 1, if we take it, okay, 90 degree from away from this, that is essentially the great circle corresponding to this one will be the one which is passing through all these. This is the way it will be passing through this great circle. Okay. And the great circle corresponding to 1 bar 0 will also be the line which is passing through this. Okay. These two intersect at 112. That is because 112 is 90 degree away from 1 bar 0, and it is also 90 degree away from 1 bar 1, and the great circle corresponding to both of them intersect at this point. So that intersection point should correspond to 112 pole. Okay. Or we can just do that. If you take this one 101, okay, and this is 011, and this is the intersection point. If we take a vector addition of this, this will turn out to be 112. Okay. And 001 and 111, if you take the vector addition of it, this point will turn out. So this point which is lying on these two lines, okay, that has an intersection will have using vector addition. There are many various ways in which you can do it, but like this we can mark more poles, okay, and this way we can construct the stereogram for 001. Okay. This is how the stereograms are constructed. Okay. But the taking the general method of that considering the general method of putting a cube at the center of the sphere, it is the nicest way in which we can visualize it and understand how a stereogram is developed. Okay. In this particular projection, what I am showing it essentially is the 001 projection is being shown. Okay. And here if you see the two circles which you can see, the ones which are filled circles, they are corresponding to the poles which are there lying on the top hemisphere. Okay. If you wanted to project the poles which are lying on the bottom hemisphere, then what we have to do it is that all those poles will be marked with open circle. That is what essentially it is being shown here. Okay. As I mentioned earlier, okay, we can, instead of taking this as that plane, I can take this plane, okay, and look in this direction, and then also create a stereogram corresponding to this pole 1 bar 1. Okay. That is what it is being. Suppose I wanted to create a stereogram corresponding to 011. One is visualizing it that way, or the other way which we can do it is once this stereogram has been done. Okay. If you remember, we said that how to rotation of poles, that we learned in that last class. So if you wanted this to come to the center, okay, 011 and 001 makes an angle of 45 degrees. So this has to be rotated along this equatorial equator line, okay, by 45 degrees it will come to a center. When this comes to the center, all other points also will be rotated by the same degree. All the poles will be rotated, because when we rotate, that entire sphere is being rotated. So this will also be rotated by 45. This will be also be rotated. All of them will be rotated by 45, and essentially this moves on the equatorial plane. Here what it will happen, this will be all moving on the latitudes corresponding to them, as we learned in the last class. Okay. When we do that, Now we can see that 0 1 1 has come to the center, 0 0 1 which was there has moved 45 degrees, has come to this point. Okay. 0 1 1 bar which was there has moved from here and reached this point. Similarly, 1 bar 1 1 was there, moved on this latitude and reached here, and 1 bar 1 0 which was there has moved and come, and which was below, okay, this plane, that has now come onto that surface, and here that 0 1 1 bar was there behind this, that has come onto this part because this 0. So, this is what the new stereogram for 0 1 1. This way also we can draw a stereogram corresponding to various directions. That is, suppose I want 1 1 1 to come, what I should do is essentially 54 degrees I should move it here, then the 0 0 1 will move in this direction and reach here. Okay. This is what is shown as an example, okay, like what I mentioned that you had one. This is for the case of 1 1 2, okay, the pole is being brought to the center. Okay, this is about 36 degree. When this is being rotated in the same direction on this equatorial plane, okay, 0 0 1 is rotated and it reaches here. All others, because the rotation axis now is around this 1 1 bar 0 in this axis. Then if we rotate around this axis, okay, this is going to be the equatorial plane. So, and these are all the latitudes. So, 0 0 1 which was there initially, it has moved and come here to this position, this is the new position. Okay. Now, we can see that all the ones which are written, the letters which are larger font, they are all correspond to the new position of the poles. That is, this is for 1 1 2 so on, if it comes to a center, these are all the positions in which the poles will be lying. But what is essentially being shown is that what was their original position and how they have moved, that is what is being shown here. This is the way in the previous view graph from 0 0 1 we have reached 0 1 1 pole. So far we have considered, we learned how to construct stereogram for 0 0 1, okay, 0 1 1, 1 1 2. Like this for any pole one can construct a stereogram. Okay. That is for a cubic system. Normally stereograms for cubic systems are available in books, or one can buy them also in a standard size, and they can be used in the analysis. Suppose the sample which we are examining in a microscope is a non-cubic system. The example which we have taken is, suppose the second phase particle is a tetragonal one, okay, and the C/A ratio turns out to be 0.833. Okay. Then what is going to happen is that angular relationship, okay, we have to calculate using the value of A, B and C. Okay. So, for each crystal, depending upon the lattice parameters, okay, angle between the planes will change. This table illustrates that. Okay. Between 0 0 1 and 1 1 0, it is essentially 90 degree for cubic, and all other planes it is 45 degree. Here if we see for this particular case, between 1 1 0 and 0 0 1, they are perpendicular to each other, it will be 90 degree. But with respect to 0 1 1, instead of 45, now it is 39.8, okay, 1 0 0 also 39.8, but with respect to 1 1 1, it has become 49.7. With respect to 1 0 0 also we can calculate it. Now you see that between 1 0 0 and 1 1 0, this is 45 degrees, okay, whereas with respect to 1 0 0 and 0 1 1, it is 90 degree, but then with 1 0 0 and 1 0 1, it is 50.2 degree. Now we can make out that the angles are different, though the indices of the plane normals, if we consider, are the planes, they remain that same. Okay. So, once we have a table like this, like we constructed the stereogram, using this information we can construct a stereogram for this tetragonal crystal also. That is what is essentially shown here. Okay. Here what is going to happen between 0 0 1 and 1 0 0, it makes an angle which is essentially of around 39, that is from 0 0 1 and 1 0 1 it is 39. So, since it is lying on a longitude, we can directly mark it. Okay. Between 1 0 0 and 1 0 1 it is 50. So, this is the point which it will come. Okay. Similarly, between 100 and 110 was 45 degree, 001, okay, and 110 is also 45 degree. Okay. Then between 001 and 011, if we consider, it is again 39. Okay. Between 010 and 011, it is going to, so this point, these blue lines, the intersection represents corresponding to the tetragonal one, and for comparison I have kept the stereogram corresponding to a cubic system also here, and now you can make out that this is the point which corresponds to 111 plane, okay. And in fact, if you look into the crystal structure along 111 direction, now the threefold symmetry is lost, okay. So this way, now when we know that the pole corresponding to 100 is there, okay, now we can draw the corresponding to this particular pole, the great circles which we can draw 90 degree corresponding to that, okay. But what we will find is that what is going to be the angle between this and this, one has to be quite careful about it, okay. But in the diffraction pattern, from this particular point 90 degree, if we draw a great circle, those are all the ones on which all the diffraction points will be coming. But essentially what is important is that this particular pole is a plane normal, but the direction in the crystal, if you consider 101 direction in a crystal, will be appearing it at some other point, okay. That is what is shown in the next view graph. So essentially one has to be careful, because compared to a cubic system, one can just visualize the complexities which are creeping in, okay. Because here if you see it, for the planes, okay, this is the great circle corresponding to them, okay, for non-cubic system, and for the directions we can see that this is how, because the indices remains the same, but you find that the poles corresponding to plane and the poles corresponding to a directions, they are not that same, okay. This fact has to be kept in mind when we wanted to use stereogram for analyzing the diffraction pattern, okay. These aspects one could not go into all the class, because this has to be one which has to be worked out in a tutorial class where one has to work it out for oneself, okay. This you will understand when you deal when you work on a system which contains second phase particles, or systems which have crystal structures which are non-cubic, okay. So far whatever we have talked about is how to generate a stereogram by doing calculation manually, how it can be generated. But the same thing can be done by writing some code, and a software can be developed which can do that. And this is available in the open source softwares are available, free softwares or download softwares are available which can be used, and you just mention that instructions, they will tell how to do this rotation and all this analysis which has to be done, everything will be which can be done. But that will look like a black box unless you understand what it does, for which trying to develop a manual that is develop stereograms manually and using them, that way you gain an experience, then the confidence in your analysis will increase considerably, okay. Now what I will do it is how this stereogram is used in the representation of point group symmetry, okay. This you might have seen when you have studied crystallography, okay, how point groups are represented. Essentially we will again consider a sphere, okay, so that the visualization becomes much easier, okay. Okay. suppose we have a pole here, okay, and this plane is the mirror plane. So, if this mirror plane is there, this pole will be reflected and it will be coming here, correct. If this is the viewing direction in which we are viewing it, okay, then what will happen is that on the viewing plane this mirror plane will come and these two will appear. That is exactly what is it being shown here. That is this is the primitive circle and this is a pole and the mirror plane is passing through this axis, x axis, and then this gets reflected and it comes. Suppose you assume that this is the mirror plane, equatorial plane, then this point will be reflected and it will be coming somewhere here at the bottom one, okay. But you know that the pole which is going to be there on the bottom one, okay, will not be represented on the stereogram generally. So, how we represent it, as we learned in the last class, that is represented by viewing it from here, okay, and then using an open circle. So, if you do that, this will be just superimposed on top of that, and that is precisely what is being shown in this particular case, okay. And this thick line essentially indicates that on this primitive circle is where the mirror plane is also there, okay. And another important factor which you should know, that is if we consider for this one, this is the viewing direction. So, essentially when it cuts this surface, okay, the cut section in the equatorial plane has to lie within the primitive. That is also is what is being represented and shown here, because you can see that all the poles which are being marked here, they are all within this circle, okay. And suppose an inversion is taking place across a point, okay. This is what also we learned, that is across the center point you invert it and show it with an open circle, okay. That is how it is represented. In fact, whatever we have learned in the previous class, okay, that is being used, okay, in the point group representation. Suppose it is a rotation around this one, two-fold rotation is there, then what it will happen? So, this point, if it is rotated by 180 degree, okay, in the same hemisphere it will rotate and come to some other point, okay, and that is essentially what is, but it should be moving along a particular latitude when we rotate it. So, it has to be that is what essentially is being shown. These projections are, if you look at it, is essentially on like a polar projection. So, it is being moved from here and the same latitudes are concentric circles, it is moved from here to here, okay. This is for 2 where the two-fold rotation axis is lying on this axis. Then when we do an 180 degree, what is there going to be on the top hemisphere, it will go to the bottom, okay. Then it will be shown with an open circle, okay. Similarly, a 4-fold rotation if you consider, so it will be all on the top circle, okay. This is what it will be rotated, okay. Similarly, various other symmetry operations are seen, and this is how the various point group symmetries are represented on a stereographic projection. In fact, here if you look at it, this particular point for a cubic system, whether it is 2, 3 or here if you see it, 1 on 1 has got a 3-fold symmetry, okay. These are all the points which are 3 points which are going to lie, and they make an angle which is equidistant from this one. That is the locus of a circle which has to be drawn on this, and we learned the last class how to draw the locus of a circle. So, all these things has been learned essentially to effectively use stereogram to represent different planes and directions in the crystal, okay. And if it is M3 bar M, okay, then what is going to happen is that every point there will be a reflection. So, now you can see that around this locus circle, okay, corresponding to that we have every point there is a reflection, it is getting reflected along these particular planes, okay. So, in short you can make out that the basic things which we have learned, how to use stereogram, okay, all those techniques are being employed to represent point group symmetry and stereographic projection. Okay. Another one which I mentioned, though I said that I will not go into a detail, but I just wanted to mention this, that orientation relationships, that is, if we use that is, we can use the stereographic projections, standard projections which are there, to analyze and index the crystal structures. And if diffraction pattern contains diffraction reciprocal lattice information from both the matrix as well as the second phase particle, by analyzing them, okay, using stereographic projection, we can get information about the orientation relationship. This is one which is has to be actually worked out on a specific system, and beyond the scope of this lecture. This you will be learning when you are looking to a sample in the microscope and you face a situation where this sort of analysis has to be done. Another aspect in which stereographic projection is being used, another area is when we deform a single crystal of a sample, okay, the crystal is oriented along a particular direction. Okay. We know that when we deform a single crystal, okay, for example, if you take a cubic crystal or FCC crystal, we know that there are 12 slip systems are there, okay, with respect to direction which we have chosen for deformation. Okay, we can find out what is going to be the Schmidt factor on each of the slip systems, okay, and whichever slip system has got the largest Schmidt factor, that is the one which is going to be activated. Okay. If the direction of loading is along some specific directions, then more than one slip system can have the same Schmidt factor, then both the slip systems could be activated. But what is essentially important is that suppose it is along a random direction, one slip system is activated, how the slip systems change during deformation, okay. All this information we can get it from looking at the stereographic projection. This is just one example which I had given. Okay. In the mechanical metallurgy course, you will be studying all these aspects. In a single crystal, okay, we assume that only single slip system is activated. So, this is the way it will be deforming if it is not being held rigidly. Okay. If it is being held rigidly, then what is going to happen is that since it cannot translate, a rotation of the slip system has to take place. So, that is what essentially is being shown on the stereogram. This is P is the loading direction, okay, and for which the 111 is the slip plane, okay, and 1 bar 01 is the direction of in which the slip occurs, which has got the maximum Schmidt factor. This is the one which gets activated, okay. But as the sample is being held rigidly, there is a rotation which takes place, because of which it will try to move and reach this point. When it reaches this point, okay, the Schmidt factor for the slip on 111 plane as well as 1 bar 1 plane, both of them are equal. So, both the slip system will be activated. Okay. Then essentially what happens is the direction of the loading gradually changes and reaches here. That is the point at which the sample fracture will occur. But what is essentially important is that looking at the stereographic projection, okay, or using the stereographic projection, we can tell, okay, how which slip system is activated first, what all other slip systems will be activated during deformation. All these information we can obtain. Okay. This is beyond the scope of going into detail, beyond the scope of this lecture. So, but I had just mentioned it so that you will remember in situations where you find when you are working with single crystals, okay, you can use stereogram to get information about which type of slip system will be active when we deform a sample. Okay. What I will do it is that I had given a brief and overview of a stereographic projection, okay, basic construction of stereogram, okay, and how to use it to measure angles at between planes and directions, and how to rotate the crystal, okay, all those basic operations I have taught, and then how to generate a stereograph for cubic system as well as for non-cubic system, okay. The next aspect is how to use it. That part of it you will learn it when you operate microscope, okay, look at microscope and analyze your results. I will stop here now.